because otherwise they are not going to end the network.
So the speaker is Carlos Cardona.
All right, thank you very much. It's a pleasure for me to be again talking in my own workplace. I think many of you have already heard about this talk before. I have something even newer to talk about it, but UT1, which is the one which I made, is going to talk about this on Friday. So I would rather prefer to talk about my previous work this year. So this is on some work I have been doing this year, early this year, with some of my collaborators, Humberto Gomez, Bofen, Region 1, and myself. So let me just skip the outline. And this is related to the computation of the scattering amplitudes. So I don't think I even have to motivate why it's important to understand deeper scattering amplitudes, but let me just say that the scattering amplitudes as the main observables we have been using to connect our physical models to the experiment. And we have been doing that for a long time by using perturbation theory to Feynman diagrams. Feynman diagrams are very, very, very beautiful objects, but unfortunately they are not efficient, or maybe they are not as efficient as we would like them to be. Simple processes are in pure Young mills are six particles scattering account 200 and something diagrams that we need to sum up. So new methods cry out to be developed in order to make this computation more efficient, but even more to make properties of the theories more manifest, like gauge invariance and actually global invariance and things that are very hidden in the Feynman diagram approach. So I essentially will concentrate on a very recent formalism, which is known nowadays as CHY formalism, and I will try to be more pedagogical instead of technical. I think that would be more practical for most of the listeners. So this historical trace back to the 80s, where Parker Taylor studied scattering amplitudes for pure Young mills, and then by making just a brave work of some hundreds of Feynman diagrams, they realized that the simplest amplitude in Young mills, which is called maximal Harris violating amplitude, which consists of a bunch of gluons with two of them of different helicity of the rest of them. So it turns out that by sum out and study all these Feynman diagrams, they managed to write all those Feynman diagrams in a single line, in a very compact way, by using something that before was called magic variable. So this is a particular parametrization of the momenta, allows to see this very clearly. So this was very interesting by that time, but it took 10 years until someone else, naive, realized that actually this same formula corresponds to, it's equal to a correlation function of a best Witten on a sphere. So that's like one of the first, maybe not first, but one of the connections connecting Young mills with some kind of extreme behavior. But then it took 10 years more for Witten to realize that actually this can be generalized to general helicity, not just spin 1 particles, but to general helicities. And it's essentially find a space where the dynamics of the on-shell objects are natural. So if we write in 4 dimensions the momentum of massless particles as a product of 2 spinors, it turns out that this parametrization of the momentum encode implicitly the mass shell condition of the particle. So this defines a natural space where the on-shell objects live. Anyway, so maybe there is people that is more familiar about this formalism than me, but let me just mention that this gives rise to this huge momentum twistor hype that has been used successfully in N=4 supergiant mills, and I have done a lot of progress on that. So my question is, can this stringy picture in 4 dimensions can be upgraded to general dimensions, more other than 4, and more importantly, to other theories other than giant mirrors? So the essential rule is we want to start from some stringy kind of picture where we have, for example, for 3 level we have a sphere with punctures on it, which is these red dots represent punctures of the sphere, and we want to embed or somehow to map this sphere, this string, to the null cone. So what is the space that encodes this information? So one way to do that, okay, this was made by Cachazo and Joan. Let me just, I will go back in just a second. So one way to do that is that you for example, define the momentum of external particles as the residues of some polynomial, some analytic function on the sphere. So as you see, the residues of this integration here is nothing but the momentum of the external particles. So I have done nothing on that. So meaning that this analytic function, when I evaluate this analytic function over the punctures, I satisfy the null condition, but I want to satisfy the null condition on the whole sphere. I want to map the whole sphere to the on-shell, to the null cone. So if I impose that by solving this equation, in terms of the coefficients of this guy, anyway, I found this restriction. So this is the map that connects the momentum living on the null cone to the punctures of the sphere. So this condition here tell me how this map is defined. So by finding that map in here, I will define an object that let me call for now S matrix, which is such as I have to find an object such as when I evaluate that object on the solution of the scattering equation, which is the map from the sphere to the null cone, then it will give me, so this is not this at the end of the day, this is nothing but the sum over the solutions of this restriction. So this is a way to write an S matrix as a sum over solutions of some set of equations. And this is very stringy actually. Okay, let me motivate from the string point of view. From the string point of view, you can think that you start from a string theory, any string theory you like the most, and then you study the high energy behavior for a scattering of 4 strings. So there is 4 strings scattering, and then you take the large energy limit, and then in the large energy limit, the integration over the world shell will be dominated by a saddle point, and then this saddle point occurs just in this thing. So this saddle point is like the dominant part of the when we have to integrate with the worksheet. So this is the saddle point for the high energy behavior of the theory. And if you are still thinking in a string theory, this is going to be the correlator between the vertex operators on the sphere. There is actually an extreme theory realization of this more explicit, but I don't want to mention that. So in summarizing, this piece here carries the information of the dynamics, and this piece here, capital I, carries the information of the particular theory. So carries information about the couplings, the global and gauge symmetries, and the helicities of the particles. So now the question is okay, so there is 2 questions to answer: how I deal with this and how I deal with the capital I. So how I deal with capital I. In order to deal with capital I, we can start from string theory, for example. So you for example, can start from the known cases in string theory, like Jan mills. We know that when we take the alpha prime going to 0 limit of a string theory, we have to recover Yang-Mills, and as a matter of fact, we do. So by looking at that limit, we can see how the correlation function, this capital I, behave, for example, in 10 dimensions. And then once you have this for Yang-Mills, you can start doing dimensional reduction, right, from Yang-Mills to obtain theories in lower dimensions. But we can do better, actually, because this formulation here doesn't restrict us to string theory. It just says that this guy here, this capital I, has to, the only restriction is that this guy need to have the right properties on the SL2C transformations that leave the moduli of the sphere with punctures invariant. So that's the only thing I have to ask. So I can define any function which satisfies that property. I compute that object, then I compare that with my known theories, and I can actually read what theory I'm looking at for a particular capital I. Even more, once I have discovered some of the i's I can describe with this formula. As you guys know, in string theory, the correlators always split in z bar. They always split like in products of two things. So this capital I also does. So this guy factorizing in kind of a product of two things, then I can start mixing these two things. Once I know what is the integral for Yang-Mills, for example, I can take the integral for Yang-Mills and multiply for another integral for Yang-Mills, and we know actually what is the result. Yang-Mills times Yang-Mills is gravity, and I can start making a lot of mixing. So anyway, this exercise has been done the few last years, and let me just mention few members of this family of theories that we can describe with this formula. Is a biadjoint, cubic scalar, quartic scalar. Actually, there is a very recent proposal for phi to the n. We can also describe Einstein gravity for in general dimension, Yang-Mills, Einstein-Yang-Mills, Einstein-Maxwell, Dirac-Borinfeld, nonlinear sigma model, Yang-Mills, coupled with scalars. And this is a very interesting old theory, but to just start calling the attention very recently, which is Galileo. It's an effective theory similar to nonlinear sigma model, an effective theory for scalars. Anyway, so this is a kind of a special set of theories. So in general, the integrants, all of these theories are, the integrand corresponding to all these theories in general can be written as rational functions in terms of these variables, which let me call distances, which are like the distances between punctures of the sphere. And let me just mention some example. For example, biadjoint cubic scalar is given by this kind of the product. You see all factors like a product, so it's like the product of two things. For this theory, is the same guy